Chapter 17, Quantum Vibration, Section 17.2, Quantum Vibration of Harmonic Oscillators. The time-independent Schrodinger equation for the two-particle harmonic oscillator is this: H psi equals E psi, and H psi equals the kinetic energy operator applied to psi plus the potential energy operator applied to psi. The potential energy is half kx squared, as stated in Hooke's law. Now, kinetic energy operator, it's negative h bar squared over 2 mu d squared over dx squared. Mu is the reduced mass. 1 over mu equals 1 over m1 plus 1 over m2. We can also take the reciprocals of both sides. Then mu is equal to m1 times m2 divided by m1 plus m2. The solutions for this Schrodinger equation is this. It's fairly complicated. We have many solutions. This n can be 0, 1, 2, 3, 4, 5, etc. A sub n is the normalization factor. And h stands for a Hermite polynomial function. Over here we have a Hermite polynomial function of square root of alpha times x. Now, what is alpha? Alpha is the square root of k mu over h bar. We also have a Gaussian function, e to the power of negative alpha x squared over 2. So this Hermite polynomial function takes the form of negative 1 to the power of n e to the power of x squared, and then the derivatives of e to the power of negative x squared. This n can be 0, 1, 2, 3, 4, etc. And over here, we just plug in the corresponding value of n here and here. So now let's look at one example. When n is 0, that's simple. We have negative 1 to the power of 0, and then e times e to the power of x squared. And over here, it's d0 over dx0. So this is simply doing nothing. And then doing nothing to e to the power of negative x squared is itself. So this and this cancel. We have just 1. So this h0 Hermite polynomial function is simply 1. Now, what if n equals 1? When n is 1, we have negative 1 to the power of 1. We have e to the power of x squared. We take the first derivative of e to the power of negative x squared. That's negative 2x times this Gaussian function. The final result is 2x. What if n equals 2? We have negative 1 to the power of 2, and then e to the power of x squared, and then the second derivative of the Gaussian function. The second derivative of the Gaussian function is simply the first derivative of the first derivative. Alright, we can just take the first derivative of negative 2x, which is negative 2 here. We can take the derivative of e to the power of negative x squared. Again, we get negative 2x times this Gaussian function, and negative 2x times negative 2x, we get 4x squared. Alright, so and then this and this cancel, so in the end we have 4x squared minus 2. So you can see h sub 0 is the 0th order polynomial function, h sub 1 first order, h sub 2 second order polynomial function, h sub 3, h sub 4 will be the third and fourth order of polynomial function. It's just we need to kind of determine the derivatives of a Gaussian function and do some multiplication. That's it. The wave functions of the harmonic oscillators take this kind of form: a normalization factor, a Hermite polynomial function of not just x, but the square root of alpha times x, and then a Gaussian function here. Alpha is the square root of k mu over h bar. Alpha is just defined that way to simplify the expression. And a is the normalization factor. A takes this kind of form. A is 1 over the square root of 2 to the power of n in factorial, and alpha over pi to the power of 1 over 4. We can prove a sub n is equal to this, but it's extremely tedious. To prove this, we just make sure that the integral of the squared modulus of psi is 100% over the entire space. H sub n is the nth order Hermite polynomial function, so we have the form of a Hermite function like this. And then if we have a Harmonic function of not just x, but the square root of alpha times x. Well, h sub 0 is 1, h sub 1 is now 2 times the square root of alpha times x. H sub 2 is now 4 alpha x squared minus 2. The first three wave functions of the harmonic oscillators are thus here, here, and here. They are just a normalization factor multiplied by the Harmonic polynomial functions multiplied by this same Gaussian function. Now we're going to look at some normalized wave functions for the harmonic oscillator. Again, the wave functions take this kind of form, and if we normalize those functions, we obtain the expression of a sub n. So over here, when n is 0, the ground vibrational energy, we have the normalization factor to be alpha over pi to the power 1 fourth, and the Harmonic function is just 1, and then we copy the Gaussian function here. And now, what if n equals 1? Well, again, we're gonna get more and more complex expressions, because the Harmonic polynomial function now takes an order of 1, an order of 2, an order of 3, etc. And also you can see the normalization factors are fairly complicated, but usually determining the values of normalization factors is tedious, but not very important, because if you want to determine the physical property given a wave function, the normalization factor does not play a role. Alright, now let's just look at the shapes of those wave functions. First, psi of 0. Psi of 0 takes this kind of shape. It's just a Gaussian function. It's just typical Gaussian distribution. Now let's look at the shape of psi sub 1, the first excited vibrational energy. Alright, you see there's a node in the middle. Why? Because you see this x here. When x equals 0, we have a node. Psi of 2, we have two nodes, one here, one here. Why two nodes? Well, we can set this polynomial function to 0, then we get two roots. Over here we can see when x squared is equal to 1 over 2 alpha, we have positive and negative square root of 1 over 2 alpha, two roots. Psi of 3, three nodes. Why is that? Look at this. The first node is when x is 0. Alright, and then two other roots, they correspond to plus minus the square root of 3 over 2 alpha. Alright, so I think they are here and here, three roots. And of course, when n increases, we get more and more nodes. When n is 4, we see 1, 2, 3, 4. And then it includes 5, 1, 2, 3, 4, 5 nodes. As the quantum number increases, the number of nodes increases as well. 0 nodes, 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes, 7 nodes. And also, if you just look at the shape closely, don't they look like the wave functions of a particle in the box? It's like a sine function, the first sine function, the second sine function with a node, the third sine function with two nodes, and then 4. So this one looks like a sine function, right? So with two wavelengths, you have one wavelength here, another wavelength here, remember? So they do look similar to each other, because if you think about it, if you examine the Schrodinger equation of the harmonic oscillator, if you examine the shape of this potential energy, it's almost just like an energy barrier, right? Energy barrier. You have a particle confined by this barrier. Well, there are two differences. One, this barrier is not a infinite energy barrier, and also this barrier is curvy. When you have a particle in the box, it's like just a vertical line on the left, a vertical line on the right. So two differences, but both are like particles confined within barriers. So it's not a surprise they have similar shapes. Alright, let's get back to the vibrational energy. It turns out the vibrational energy is n plus 1/2 times h nu. So when n is 0, that's so-called 0-point vibration energy. The lowest possible vibration energy is 1/2 h nu. And when n equals 1, we have 3 halves. When n equals 2, 5 halves. When n equals 3, we have 7 halves h nu vibrational energy. So energy goes up, and we take this kind of form. The time-independent Schrödinger equation for the two-particle harmonic oscillator is h psi equals E psi. H is kinetic energy operator plus potential energy operator. In the ground vibrational state, we have a ground vibrational wave function, which is a Gaussian function here. A is the normalization factor, alpha is the square root of k mu over h bar. Now we'll just prove this. We'll apply this Hamiltonian to this wave function, and hopefully we'll get the corresponding vibrational energy multiplied by the wave function. So we'll do this. It's completely mathematics. I'm applying the kinetic energy operator to the wave function here, potential energy operator to the wave function. Alright, here we take the second derivative of a Gaussian function. It's the first derivative of the first derivative. So I'm taking this normalization factor out for simplicity, and I'm going to take the first derivative of this Gaussian function using chain rule. It's negative alpha x times the Gaussian function. So over here, this part is easy. I'll just copy that here. Now I'm going to take negative alpha out, and we got a times alpha h bar squared over 2 mu. And then we'll take the first derivative of this. I copied the kinetic energy part here. Now what's the derivative of this one? Product rule in calculus. The derivative of x is just 1, so 1 times this Gaussian function here. What's the first derivative of this Gaussian function? We use chain rule. It's negative alpha x times this Gaussian function. There's another x, so it's negative alpha x squared. So we have this expression. We copy the kinetic potential energy term here. And now finally we need to plug in the expression of alpha. Alpha is the square root of k mu over h bar, so this is alpha. Alright, and we just replace this with square root of k mu over h bar. Alright, so we expand 1, 2, 3 terms here, here, and here. We do need to clean up a little. You see this mu here and mu here, they partially cancel, and we have h bar squared over h bar partially cancel. Over here we have k and mu on top and mu on the bottom, so we have a k left. We have h bar squared and h bar squared on the bottom, so we cancel. We do all those cancellation or other simplification, we get this expression of 3 terms. Apparently the second term and the third term cancel. Only the first term here, and I'll just copy that to here, and we can express this as 1/2 h bar times the square root of k over mu, and then multiply by the wave function. And again, 1/2 h bar times the square root of k over mu. Well, it's actually 1/2 h nu, or you can say it's 1/2 h bar times the angular frequency. Alright, the angular frequency is 2 pi times the ordinary frequency nu. So over here, chemists usually write 1/2 h nu. Physicists usually write 1/2 h bar times omega. So, but they are the same. 1/2 h nu equals 1/2 h bar omega. Nu is 1 over 2 pi times the square root of k over mu. the angular frequency is just the square root of k over mu. The time-independent Schrodinger equation for the two-particle harmonic oscillator is this. We verified that this is the eigenfunction, and A is normalization factor, alpha is defined to be the square root of k mu over h bar for convenience, and we have derived the 0 point or lowest possible vibrational energy, which is half h nu. On the previous page, nu is 1/2 over 2 pi square root of k over mu. Again, this is also 1/2 h bar omega, where omega is 2 pi times h nu, and h bar is h over 2 pi. Given the wave function, we can always compute the expectation value of its physical properties. Now let's compute the expectation value of the potential energy and kinetic energy, or sometimes for simplicity we just say average potential energy and average kinetic energy. We resort to quantum mechanical postulate 4, which is this. This is the average property, and we have two integrals, one on the top, one on the bottom. They look similar, except this psi should be O psi on top. O psi is the O operator applied to psi. So we can do the calculation for the average potential energy. We have the wave functions on the bottom, the wave functions on top, and then this is potential energy applied to wave function. A and A cancel, A and A cancel. We do some simplification. We take half k out. Really, it's just the division between the two integrals. On top you have x squared here multiplied by the Gaussian function. On the bottom you just have this Gaussian function. So after you do this, you get something in terms of alpha, and then you combine half k with alpha. You will end up with a quarter h nu. And again, alpha is defined to be the square root of k mu over h bar. What about kinetic energy? You can just apply the kinetic energy operator over here to the wave function. So on top, it has to be the operator applied to the wave function here. Alright, and then on the bottom it's just the wave function. Here it's just wave function, wave function. This is non-trivial, so I'm gonna just neglect all those steps. You'll get 1/4 h nu as well. So the vibration energy is 1/2 h nu. It's evenly distributed to the potential energy and kinetic energy. They all have 1/4 h nu on average. Again, this is just the average value. Can we determine the exact potential energy? No. Can we determine the exact kinetic energy? No. It's just this wave function is not an eigenfunction of the kinetic energy operator, not the eigenfunction of the potential energy operator either. So there's no way to determine the exact value of the potential energy or the kinetic energy. But we can determine the sum, which is half h nu. We can determine the average potential energy, which is 1/4 h nu. And actually, the average kinetic energy is simply the sum minus this average. We get 1/4 as well. Now let's look at one more solution. Let's look at the first excited state with such wave function. We have one additional polynomial function x here, first order, and then multiplied by the Gaussian function. Alpha is the square root of k mu over h bar. Again, we apply the kinetic energy operator to the Gaussian function, potential energy operator to the Gaussian function. The math is more tedious. You just take the second derivative of this whole thing. We need to use the product rule already over here, and this is a potential term. Second derivative, even more complicated, but we can do it. We combine x squared and x over here, And now we have 1, 2, 3 terms. We can just kind of expand them and do some simplification. And over here we have another term over here. And in the end, if you just clean up everything carefully, I think you will just get something like this. In the end, it's going to be 1.5 h nu multiplied by the wave function. Sorry about this kind of mathematical derivation. It's really tedious. Honestly, I often use Wolfram Alpha to do those kind of derivation for myself. We get the eigenvalue, which is 1.5 h nu. Nu is 1 over 2 pi times the square root of k over mu. Again, you can rewrite this as 3/2 h bar times omega. H bar is h over 2 pi. Omega is nu times 2 pi. So it's just the different flavors. This is more like chemist's flavor. And if you use h bar times omega, more like physicists. Now we're going to talk about the tunneling effect, because you can see there is indeed a energy barrier. The potential energy is half kx squared. So if the total energy is smaller, then the potential energy supposedly will get a negative kinetic energy, and that's classically forbidden. However, we observe quantum tunneling effect as well. We observe the vibration may exceed the classical region. So when does that happen? Obviously when the total energy is less than the potential energy, and the total energy is n plus 1/2 h nu. So when this is less than 1/2 kx squared, you have the so-called classically forbidden region. Theoretically, the tunneling effect is just non-zero as long as this x is finite. Let's look at one example. The simplest example is the ground vibrational state. Alright, and then the total energy is simply 1/2 h nu, that's it. And then when the potential energy is greater than the total energy 1/2 h nu, we have a negative kinetic energy, and that's called quantum tunneling. It's in the classically forbidden region. We can even solve this. We can see x is greater than the square root of h nu over k, and also you can rewrite this as the square root of h bar over the square root of k mu. Why did I write this? Well, it happens that this is the reciprocal of alpha. Alpha is defined to be the square root of k mu over h bar. So when the value of x is greater than alpha to the power of negative 1/2, we see tunneling effect in the classically forbidden region. All right. So the spring is overly stretched. So again, over here you can see that these displacement can stretch actually over a very long range, and if you have a higher energy, the tunneling effect is even more significant. All right. So this is probably less significant than this. All right. We have more significant tunneling effect if you have a larger energy. All right. If you have a larger energy.